Let's use our knowledge of transformations to sketch graphs of more complicated exponential functions and identify their domains, range, and asymptotes. So what we'll do is we'll identify what is the original function that is being transformed to get this function here, which is 2 to the x minus 3 plus 1. We'll sketch the original function, transform it, and we'll make observations about how the transformation affects the domain, range, and the asymptote. So here, the original function is doing 2 to a power. F of x is equal to 2 to a power. And just as I've done previously, what I'm going to do is I'm going to take my function 2 to the x minus 3 plus 1, that's g of x, and I want to write it in terms of f of x. So going piece by piece here, I have 2 to a power, which is the same structure as f of x, except the power is different. It's x minus 3. That means that instead of doing f of x, I'm doing f of x minus 3. And then outside of doing 2 to this power, I have a plus 1. And so we see that this is a right shift by 3 and an upshift by 1. Right shift by 3, upshift by 1. Now let's go ahead and sketch the graph of 2 to the x and the transformed function. I have some graph paper here. So 2 to the x, that goes through 0, 1, 1, 2, 2, 4, negative 1, 1 half, negative 2, 1 fourth. And if you wanted to check any of these, so for example, if you wanted to know what the y value is at negative 2, just do 2 to the negative 2, and you get 1 over 2 squared, which is 1 fourth. We'll go ahead and connect all of these, and we'll get a sketch of the graph of 2 to the x. Now let's go ahead and apply our transformation. So we're going to need to go to the right by 3, if I recall correctly, right shift by 3, up by 1. So we'll take our points here, for example, 2, 4, move right 3, 1, 2, 3, up 1. 1, 2, move right 3, 1, 2, 3, up 1, and I'll do this a little quicker for the others. 1, 2, 3, up 1, and we'll go ahead and connect with a smooth curve. I think I need this last point here, negative 2, 1 fourth, 1, 2, 3, up by 1, and this would be the sketch of my graph. Let's go ahead and erase some scratch marks here. And I think before we move on, it's worth making the following observation. If you have some point on the graph, let's say very, very close to 0, and by 0 I mean y equals 0 here, then let's think about what's going to happen when we transform this point. It's going to move right 3, 1, 2, 3, and it's going to move up by 1. Now if you have a number, let's call it, I don't know, z, and it's very close to 0, and you add 1 to it, then the result is going to be a number very, very close to 1. So if we take this y value that's very close to 0, move it right 3, the y value will still be close to 0. We move it up by 1. It's going to be a y value very close to 1. And practically what that means is, since we have a horizontal asymptote at y equals 0, that means that the y values get very, very close to y equals 0 for the original graph, for 2 to the x. What that means in terms of the transformed glass, or rather the transformed graph, is that any point very close to this horizontal asymptote of y equals 0 will get close to the new horizontal asymptote of y equals 1. And that might not be too hard to digest, if you will, because think about what we're doing. We're taking all of the y values and we're adding 1 to them. So it makes sense that if you had a horizontal asymptote, it would move up by 1. So in general, if you have a vertical transformation that is a shift, so if you have a vertical shift, then that's going to shift the horizontal asymptote by that amount. So if you had a vertical shift down by 2, the horizontal asymptote would move down by 2. Okay, so we have a horizontal asymptote y equals 1. That was the last thing that was asked for, so we're going backwards, but that's okay. Now let's try and figure out the range. Remember, the range is all the y values, and for the original graph, let's make this a bit uncluttered. For the original graph, which let's go ahead and make that yellow. So for this original graph, we have a range of all numbers bigger than 0. It's because every y value that's bigger than 0 gets hit by the graph. Again, you can test that by drawing a horizontal line at any y value, and if you get a crossing, that tells you that that y value is in the range. Now, for our transformed graph, 2 to the x minus 3 plus 1, everything gets shifted up by 1. So if we think about drawing horizontal lines and asking if we get intersections, if we draw a horizontal line at a y value bigger than 1, we do get an intersection, but now, since all of the y values are moved up by 1, we do not get an intersection with the graph 2 to the x minus 3 plus 1 if the y value is less than or equal to 1. The result is that the range is going to be all numbers greater than or equal to 1. So y greater than, all y values bigger than 1, not bigger than or equal to, because the y value 1 is not attained by the graph. Or in interval form, which is typically how we denote what ranges are, it would be 1 comma infinity. And again, one can make reasonable sense out of this. The old range was 0, infinity. These were all the old y values. And what did the transformation do? Well, one part was moving the graph upwards by 1. And so that's going to increase the range by 1. So that's why we have this 1 here instead of this 0. Okay, finally, let's ask ourselves what the domain is. Figured out the range, we figured out the asymptote. What's the domain? And here the answer is a little simpler. In the old graph, 2 to the x, you are able to plug any x value in to this graph and get an output. And that's exactly the same fact that's true for 2 to the x minus 3 plus 1. Any x value you take, you can put into this function and get an output. And what that means is that the domain is minus infinity comma infinity, all real numbers.